I now call to order the Society's 2,402nd meeting in the 148th year since its founding in 1871. Good evening, everyone.
Good evening.
My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members and guests to tonight's lecture by Todd Coleman in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C., including our members and friends around the world who are watching the live stream of tonight's meeting on PSW Science's YouTube channel. We will begin with a few announcements, a reading of the minutes of the President's lecture given by Lee Cronin at the 2,401st meeting. We will then turn to this evening's lecture, followed by a question and answer period. Thereafter, I will present a small thank you gift to our speaker, make a few closing announcements, and then adjourn the meeting to the social hour. Please join me in thanking the sponsors of the 2018-2019 lecture series, the Policy Studies Organization in cooperation with the American Public University, and a generous anonymous donor. Thank you. I am pleased to announce that the following new members have been elected to the Society. Wes McDermott, a consultant with Fox Kisser, interested in biotechnology, medicine, renewable energy, and astronomy, who comes to PSW through the web and the PSW website. Ryan Harris, a recent graduate in applied mathematics and a former telescope operator, interested in fluid mechanics, astrophysics, and combinatorial mathematics. And tonight's speaker, Todd Coleman, whose background and interests will, at least in part, be clear to you from tonight's proceedings. Please join me in welcoming them to membership. If any of our new members are here tonight, please see me to get your signed volume 1 of the PSW Bulletin, which is given to all new members. It's useful because it explains why the society was named what it was named, and also lists all of the original members of the society and their reasons for founding it, and also has the minutes of the first 50 or 60 lectures. Recording Secretary James Heelan will now read the minutes of the 2,401st meeting and the President's lecture by Lee Cronin on digitizing chemistry, delivered here at the Cosmos Club on January 11th, 2019. James, podium is yours.
Thanks, Larry. Hi, good evening, everyone. On January 11th, 2019, President Larry Milstein called the 2,401st meeting of the Society to order at 8:01 p.m. in the John Wesley Powell Auditorium of the Cosmos Club in Washington, D.C. He announced the order of business, that the evening's lecture would be live streamed on the internet, and welcomed new members to the Society. The minutes of the previous meeting were then read and approved. President Milstein then introduced the speaker for the evening, Lee Cronin, Regius Chair of Chemistry at the University of Glasgow. His lecture was titled, Personalized Drugs on Demand, the Digitization of Chemistry. Cronin predicts a revolution in chemistry that will dwarf the recent revolution in digital computing. In Cronin's view, chemists have been constructing molecules in the same time-consuming, labor-intensive way for 200 years. As a result, discovery and production of new molecules remains slow. Chemistry hardware is expensive, not modular, not flexible, and not connected. Chemistry databases are not easy to access, and chemistry synthesis and discovery is time-consuming, step and yield limited, and not always reproducible. Cronin says these problems can be overcome by inexpensive robotics and a concerted effort to universalize the language of chemistry. He began with the premise that chemistry is merely building blocks added together in a sequence to produce molecules. By universalizing the language of sequencing instructions, the instructions for producing equipment, and making these instructions readily available, chemists could mechanize molecule production anywhere in the world. Indeed, in 2017, Cronin published in Nature the first chemical discovered using AI. Cronin's team is now developing the digitized processes to make drugs on demand. The goal was to design a system that could be easily constructed and could manufacture a drug by any layperson. As proof of concept, Cronin's team coded a program using standard CAD software packages for 3D printing the basic chambers and connections to manufacture baclofen. They then wrote plain language instructions, like a cooking recipe, for a user to follow specific steps for inputting reagents and producing 70 milligrams of baclofen as the end result. Cronin says scientists can use his method to code and to produce any drug in existence, reducing capital expenditures to near zero. He proposes using the method to produce drugs with short shelf lives and drugs that companies have deemed too unprofitable to produce en masse. The US military has also approached Cronin about use in the field. Moreover, Cronin says that by digitizing chemical production, Earth's 200,000 bench chemists will be freed to focus their skills and abilities on advancing chemistry. Ultimately, Cronin believes chemistry will surpass biology to treat human medical needs. In the question and answer period, one guest asked about the error rate of Cronin's process. Cronin said that, excluding mechanical failure, the success rate was 100%. A member asked about the potential of Cronin's ideas for machine learning. Cronin said that machine learning is multidimensional analysis reduction and therefore inherently limited. On the other hand, he said, chemistry allows for probabilistic reasoning capable of exploring the unknown unknowns. Another guest asked about the ethics of being able to produce any molecule, including opioids and weaponizable drugs. Cronin said his research was driven to help people, and that it was up to governments and communities to decide whether and how to regulate such production. After the question and answer period, President Milstein thanked the speaker, made the usual housekeeping announcements, and invited guests to join the society. At 10:13 p.m., President Milstein adjourned the 2,401st meeting of the society to the social hour. Temperature, 0 degrees C. Weather, partly cloudy. Attendance in the Powell Auditorium, 105, and viewing through the live stream on the PSW Science YouTube channel, 19. Respectfully submitted, James Heelan, Recording Secretary.
Thank you, James. Are there any corrections to the minutes? Any additions or comments? Hearing none, I will entertain a motion by a member to approve the minutes as read. I have several. And a second from a member. All members in favor? Aye. All members opposed? The minutes are accepted as read and will be posted to the website in due course. With that, we turn to tonight's lecture on wearable biosensors. And it's my pleasure to introduce tonight's speaker, Todd Coleman. Todd is Professor of Bioengineering and Director of the Neural Interaction Laboratory at the University of California, San Diego. So I'll put in a plug for UCSD. It's a really terrific place. If any of you are thinking of going to graduate school, I highly recommend it. Before coming to UCSD, he was Assistant Professor of Electrical and Computer Engineering and Neuroscience at the University of Illinois, Urbana. Todd is working to develop multifunctional, flexible bioelectronics that will enable wireless health monitoring appliances that are minimally observable and obtrusive to the user. He's an author on numerous scientific publications and speaks widely to professional and lay audiences on his work. He has given a National Academy of Engineering Gilbreth lecture, and his work has been featured on CNN, by the BBC, and in the New York Times. Among other honors, Todd is a fellow of the American Institute for Medical and Biological Engineering. He earned a BS in Electrical and Computer Engineering at the University of Michigan and an MS and PhD in Electrical Engineering at MIT. Please hold questions for the question and answer period at the end of the lecture, and join me in welcoming Todd to the podium.
Thank you, thank you. So, thank you, sir. Thank you, sir. So, I thought I'd start off by telling you a little bit about myself and how I got on the path that I'm on now. And it started when I was in graduate school, finishing up at MIT. I had this faculty position lined up at the University of Illinois, and my graduate advisor, Professor Muriel Medard, professor of electrical engineering, gave me a great piece of advice. She strongly encouraged me to not go to Illinois right away, but to call up my department chair, tell him that I want to delay my start date and to go do a postdoctoral study in something wildly different. And that's all she said. And so, mind you, I'd been trained in electrical engineering. I knew nothing biological. I hadn't taken a biology class since high school. And nonetheless, because of some of my Michigan buddies over in Boston, they kept encouraging me to take all of this artificial intelligence and applied probability that I learned and use it to benefit mankind. And so I went on a whim and tried to do a postdoc with a gentleman who's an MD as well as a PhD. This gentleman named Emory Brown practices medicine at Mass General Hospital as an anesthesiologist, does neuroscience research. But what was a link to us is that he has a PhD in statistics. And so I was able to begin to learn physiology and medicine through the lens of where I did my graduate studies. And so as I began to learn that, I was in a unique position when I moved to Illinois to now not only play in my original sandbox in electrical engineering, but to now begin to conquer some interesting questions in neuroscience. And along that path, I also got interested in some technology development. And this is sort of where our research lies right now, is at the intersection of these three areas. And so some of the applications that we got interested in start by very simple questions. And so one of the observations that I made when I got to UC San Diego is we took a look at how babies are treated in the neonatal intensive care unit. And if you talk to some of the doctors, or in particular some of the nurses, what they'll show you is that despite the fact that we're modern in many ways, when they want to check certain vitals of babies, such as temperature, it's very much a manual process where they just take this thermometer, put it under the baby's armpit. As we know, these babies cannot regulate their core body temperature at a very early age. So there's all sorts of questions about if their temperature gets too high, too low. But also this process of manually monitoring them can disrupt them and create all sorts of distress. And this is in some sense in direct opposition to lots of new work that is showing the importance of skin-to-skin contact between mother and child. Some of you may have heard of something called kangaroo mother care, the way the mom should hold the baby. So if the baby is in this unlikely position that they're in the intensive care unit and we have wires that are strapped to them, or we have these very manual ways for which we're checking their temperature, and keeping in mind they don't necessarily check temperature at a regular time. They check it when they have the opportunity to go catch these babies. Could we be missing important things? And moreover, are we disrupting the baby's ability to have this time with mom? So with these sorts of ideas in mind, our research group, in collaboration with some material scientists, demonstrated an ability to build devices such as what you can see here. So we term these devices epidermal electronics because these are electronic systems that are matched to the curvature and the bending and stretching of your skin, your epidermis. And so this was very exciting. There's many years in progress in how we demonstrated this, and we showcased an ability to measure a variety of things. So, for example, vital signs such as the EKG, the temperature, as I alluded to before, or remember me coming from this neuroscience perspective, I obviously was very interested in brain signals such as the brain waves or the EEG. And so we demonstrated this, but one of the things we always like to do is to keep ourselves honest, quote unquote. And so when you really, what it sort of reminds me of is if you guys remember Richard Feynman when he was looking at the Challenger and why the Challenger went awry, he talked to the main engineers on the ground, and they really gave him the lowdown that allowed him to understand that it was these O-rings. And there's that famous story on him in Good Morning America, putting them in the ice water, and you see, and he basically explained the mechanism. So what we realized is that we should talk to everyone, and not just physicians, but also people who are on the ground. And in many situations, we're talking about patient care that involves nurses. So we were very careful to be listening to nurses and whatnot. And one of the things that they encouraged us is that it's kind of cute that you built these devices, but there's some constraints that you need to be aware of. You ideally would like to mount these devices onto the skin using the types of materials that we naturally already put on the human body. Materials that are already FDA approved and that are routinely used in hospitals, along with a variety of other concerns. So with our research group sort of listening to the doctors as well as the nurses, along with thinking about the technological constraints, we sort of came up with this list that you can see here about what capabilities we want. So we want the devices obviously to be wireless. And one of the things that may not be obvious is that when something is mounted onto the human skin, you have to be very careful to make sure that it still can successfully wirelessly transmit, because our body is a big bucket of salt water. So there's questions there. Ideally, we want these devices to have clinical grade accuracy. We ideally want them to be low power so that we don't have this miniature device, but then a big bulky battery on top of it. As I mentioned before, we want this to have some biocompatible material that interfaces with the skin, ideally something that's already routinely used in the hospital. All the different devices for processing the data should be small, so the aggregate system is small. And ultimately, if this is not just a science experiment, we would like for us to do this in a manner that is that facilitates mass production. And so with that in mind, we sort of went on this journey of trying to think about not only just building these thin, flexible, wearable devices like what we originally demonstrated, but doing this in a manner that allows for wide-scale manufacturing processes that already are in existence. Can we somehow interface with them or be backwards compatible with them? And so that was a journey that we tried to go upon, and I won't belabor you with all the details of this, but the only point I'd like to make here with what you see right now is that the original process of how we built those beautiful systems in 2011 was very complicated. And so we had to take a silicon wafer, like the same wafers that they use to make semiconductor chips. We develop a variety of processes that are used in what's called a clean room. And the clean room is the same place where Intel makes their chips. So a lot of those processes are automated. But then we had to take the devices out of the clean room, dip them in different types of chemicals. There were certain steps where we had to manually peel something else off, then manually mount it onto something else, and to eventually get what we want. And that process of all that manually, carefully placing things created a big bottleneck. And so we had this epiphany in talking to one of the nurses that, ideally we want these devices that are integrated into the skin, but when you're inside of a hospital, there's certain types of adhesives that they use all the time. So we had this epiphany, well, why don't we embed our electronics into the adhesive and then mount the adhesive onto the body? And it turns out that once we had that mindset, it actually made our life a lot more simple. And so one of my graduate students was able to significantly reduce the steps of the process. But crucially important is that that part that required a lot of manual dexterity was completely removed. And what we can now do is use the adhesive, which we're ultimately going to mount on the body, to actually lift it off what we fabricated it on. So it's sometimes this insight from the nurses allows you to think in a way that you would not otherwise. And now we have these adhesive integrated electronic systems that can mount onto the body and still bend and stretch naturally with the body. And so I won't bore you with all the details, but the only step I want you to appreciate to get a sense of how this could be massively done is that every step of the process is basically done using the same types of steps that they use to make semiconductor chips or to make the high density displays that always go on sale right around the holidays. So all of those steps are the same types of steps that are what underneath this that have been validated and automated at high scale for high yield and low error rates. So one of the other things, as we alluded to, I mentioned, is that the importance of this being wireless and being able to wirelessly transmit when it's on the skin. So one of my graduate students who actually hails from the DC area, we went through this process of taking existing antennas, simulating these devices, and then basically designing these in software, but when they have a mesh-like structure, because if they have a mesh-like structure, it's easy for them to bend and stretch when they're in an adhesive. Then we turned around and we actually fabricated these devices and embedded them inside of adhesives. And then we actually mounted these devices on the human body and we tested. And remarkably, we got amazing performance in being able to transmit Bluetooth to, a phone over 150 feet away. So this was very exciting. And so we were able to, and notice that we're doing this while the device is on the skin in a big bucket of salt water. So other optimizations had to be done to allow for that to occur. So when we, if you stand back and you take a look at some of the requirements for wireless patient monitoring, in some sense, we've begun to solve the wireless problem. We have this biocompatible substrate. And by the way, that adhesive that we're using is an FDA-approved adhesive made by 3M that's routinely used in the hospital. It's called Tegaderm for anyone who is part of the hospital system. Tegaderm is used all the time. Whenever you get blood from someone, if you put something on afterwards, Tegaderm is what is applied. And lastly, as I mentioned, this whole mass production opportunity, because we're leveraging the same types of processes that are used to make chips and video displays. So the next step was to determine, can we get these devices to have clinical grade accuracy, low power, and small footprint. So the next step that we were interested in doing was not just building sensors, but the idea is, could you now bring your own circuit design and basically a la carte say, I want to use this device, this device, this device. I want these to be connected this way, but now I want you to put it on a flexible device. It'd be very nice if we could structure something in that way. So as long as you can tell me the part number of the chip that you want, and as long as these companies sell them in these small packaged formats, we now have an ability to do that. So I won't bore you with the details of what's being shown here, but the takeaway lesson is that we have same wafer Intel uses, a bunch of processes that are used inside a clean room, the same stuff that's used to make chips and displays. And then finally, if anyone has ever played with solder before with making circuits, we actually designed our systems that you can still use solder to place the individual chips. And then ultimately, we can still embed it inside of an adhesive. And so as an example, this is our beloved Tegaderm on the left, as I mentioned, but we can have this Tegaderm and we can have electronics on the side of here. And so we can have things like strain sensors that can, basically measure when you inhale and when you exhale. And we can have individual components made by other companies like Texas Instruments, Analog Devices, and all the while there are these, curved types interconnections, and those curved interconnections are what allow this to bend and stretch naturally with the skin. So the way I like to explain it is that it's almost as if we have a sea of flexibility with little islands of very small rigid components. And one of the things that we're very fortunate, just following the trends, it turns out that typically when you take a look at a microchip or something like that in a package, most of that is just for packaging to mount it onto something, but the actual electronics is a very, very small, minuscule component of that. Well, companies are now selling these devices not in the packages, but in these minuscule-like fashions. So these islands are getting smaller, and so we can now embed them into a sea of flexibility. So what this allows now, this is an example of one of these very small little, they're called die, and we can buy them in this package. We can use existing types of machinery that can automate the placement of these. So we actually partnered with a company in San Diego that has an automated tool, and we can create an automated tool to now have these thin, flexible, adhesive integrated systems, and now they're compatible with roll-to-roll processes. And with that, this enables scalable, cost-effective, modularized approaches to design these systems. So here's an example of a completed system. And so on this device, we have an adhesive. We have a Bluetooth chip made by a company called Cypress Semiconductor. We have a Texas Instruments temperature sensor. And this actually is a new temperature sensor that recently came out that has 0.1 degrees centigrade accuracy, which is medical grade accuracy, meets the ASTM standards for accuracy. We also have clocks, programming pads, all of the auxiliary components. And the nice thing about this is that we can embed them in different types of flexible materials to embed under the body, to place in sort of adhesives. And this was the subject of one of my students' thesis. And one of the things that he did in his thesis is he did a side-by-side comparison. And if we remember our original motivation, it was when they placed those thermometers in the baby's armpit to get their temperature. The idea being, rather than a nurse, when she has the opportunity to come by and measure these temperatures a few times of the day, what if we could just place a patch there and we can probe and get information wherever we like in an automated fashion and in a manner that's minimally obtrusive to the baby. The mom can still elicit skin-to-skin contact. So as an initial step with that, what we did is we did a side-by-side comparison with our adhesive integrated system, and we compared that against an existing on the market, bigger, clunkier button. And we wanted to do a side-by-side comparison. We developed a smartphone app to capture the information. And here's just a simple validity test. And what you can see is that the blue comes from our sensor, whereas the red comes from the off-the-shelf system. And the blue basically can get the same types of information as well as the red. And you can see interesting changes in the temperature going up, going down. We went outside to write his thesis. So believe it or not, even in San Diego, it gets cold sometimes. So this was in December. So his temperature got a little lower when he got on his bike to go outside to ride home, etc. And so we can quantify a lot of the details that we're capturing the same type of information. We also did more detailed studies in partnership with Texas Instruments. Texas Instruments basically gave us some of these chips before they were available on the market, and we did very detailed tests where we placed them into an oil bath, and we control the temperature very carefully, and we measure what we're getting with what it's getting. So we've done a variety of different types of tests. And so the takeaway lesson here is that we're on a path now where we think we can address all of these different challenges with this very simple adhesive integrated system. And so we have an ongoing study right now, actually, in partnership with UC San Francisco with their neonatal intensive care unit and their nursing program, where we're placing these devices on babies and doing side-by-side comparisons with conventional approaches. That's one of the projects that we have going on. We've also been involved in a pregnancy monitoring project to use the same type of technology to measure moms while in labor. That was with the support of the Gates Foundation. And another project that we've been working on, which might not be as obvious at first glance, but we know that skin cancer is one of the biggest killers of folks here in America. And if you take a look at places like California, Arizona, there's quite a bit of exposure to the sun. It turns out that researchers have found that a lot of that exposure, it's very much like if we've heard about football now and these, NFL players that retired, right? And they start to have all of these problems. Some of those problems actually originated when they were in high school or much earlier. And so one of the things that an expert researcher that I work with has found is that in many situations, apparently with the onset to melanomas much later on, come from playground exposure to lots of sun at much earlier stages in life. So there's an opportunity to rethink how we structure playgrounds, how we can make sure that people are not getting too much exposure that can adversely affect and put them at risk, as well as in places like California and Arizona, if you're not careful, there can be extreme temperatures and the effect that can have on the thermal regulation of children. And so we have a project where we're actually measuring UV as well as temperature in children in conjunction with schools as they rethink their playground designs. So that's one of many projects that we have ongoing with this technology. So everything that I talked about so far, so remember I went to Michigan. Everything I talked about so far is what I in some sense call playing defense. And what I mean by that is that what we're doing is we're taking existing measurement modalities that are already in use but kind of clunky, and we're miniaturizing them. What I also got interested in doing is not only playing defense, but in some sense playing offense. And what I mean by that is what if we could also create new modalities that could have clinical utility? And moreover, could we then miniaturize them to make them easy to use? It's a bit more of an ambitious goal, but it's something worth pursuing. By the way, does anyone know who this is a picture of? Tom Brady. Okay, Tom Brady went to Michigan. He actually didn't start the whole time while he was there, but so everyone knows who I'm rooting for next Sunday. So, in any case, my interest in this was in no small part because of my own life experiences. And so this is a picture of my father and myself in 2004 at a family reunion. And so it turns out in 2011, which is the same year that I moved from the University of Illinois to sunny California, in that same year, 2011, I lost my dad to pancreatic cancer. And it turns out that he lost his mom to stomach cancer. And so there's been sort of a disease of the digestive system in my family that got me to begin to scratch my head. And so as I began to scratch my head, what I was excited about being at the University of California, San Diego, as compared to University of Illinois, they both have outstanding engineering programs, but San Diego has a medical school with a hospital that trains medical students, and so there's an opportunity to interact with a lot of physicians. And as I began to interact with folks, we began to take a look at this question of the digestive system and people who maybe complain of having nausea, pain, other sorts of issues. And the crazy thing is that if you take a look at these symptoms, they can explain one of a gazillion different types of GI disorders, all of which that have different treatments to help them. And so if we stand back and we take a look, and when you first go to the family doc and you complain, it turns out it's quite difficult for them to disambiguate which of these this is, and yet it's primarily done based upon symptoms and how your symptoms are managed. And so it turns out just in the U.S. annually, it's contributed to, almost $150 billion a year. Just this long process of finally getting to an expert gastroenterologist that can help you pinpoint what your condition is, and a lot of pain and suffering in the process. And some of the people in the audience, I'm sure, have been affected. Turns out 10% of people in America are affected by these conditions. So what I found interesting about this as I began to learn more is that when we think about our digestive system, it's definitely a mechanical system because it's pushing food through to digest and secreting enzymes to break stuff down. But what you may or may not know is that it actually has a nervous system. And so there's millions and millions of neurons in your digestive system. And in fact, in China, you know what they call the nervous system of your digestive system? It's called your second brain. And it's very complex, intermingled. For example, serotonin that we think about, 70% of the serotonin in our body is actually made in our digestive system. Turns out our digestive system is actually connected to our brains via the vagus nerve and via the spinal cord. And moreover, it turns out that about 80% of the information flows from the digestive system to the brain. The digestive system is also extremely unique in that the stomach is one of very few organs that can fully function if it's disconnected from the brain. So it's a very interesting system, very complex, many neurons that are interconnected. And as you can imagine, me as an electrical engineer who turned neuroscientist, quote unquote, I got very excited to see that this complexity is here. And so if we focus and stand back and think about the electrical aspects for a second, it turns out that the stomach is a lot like the heart. We know that our heart has, there's electrical activity, which is then coupled to the mechanical contractions to get our heart to squeeze. And there's a similar phenomenon, it turns out, with our stomach. We have pacemaker cells that are aligned in our stomach, and they basically generate an electrical wave that propagates from top to bottom. And that wave, it turns out, is coupled to the smooth muscle cells that contract. And so as an example, if we take a look at one of these pacemaker cells that you see on the right at the top, it's very much like a neuron. Anyone who's seen pictures of a neuron before, where when the voltage crosses a threshold and action potential is generated, then it comes back down and it can generate another action potential. And those action potentials are what elicit the smooth muscle cells to contract. Now, what's interesting about this is that underlying baseline voltage turns out has an oscillation, a very slowly moving oscillation, 3 times per minute, or 0.05 hertz, and that wave propagates downward. And that's what couples everything, almost like an orchestra, or almost like the wave that you see at a sports game, so everything is in unison. So at a high level, what I got interested in then learning this is that what if we can take a non-invasive modality and try to have the same type of added value that is taking place with the heart? If we think about the EKG and how the EKG has been very helpful, that we can non-invasively place sensors on the chest and get diagnostic information to help someone manage their heart, could we do something analogous with the stomach, especially given that we know there's this electrical activity here? So I was able to establish a partnership with an MD gastroenterologist at UC San Diego, David Kunkel, and together our teams have been working, in fact, to solve this problem. So any good scientist or any good engineer or any good athlete for that matter, the first thing you do is, if you have an interesting question, you look back and ask, has anyone else tried to ask this question, and to see where they are so you can learn from their mistakes. And so this whole idea of being able to measure electrical activity from the digestive system and be able to use it for diagnostic purposes was not new to us. People, it actually dates back all the way back to Ramon E. Cajal, some of you know, the Nobel laureate. Those pacemaker cells are actually called the interstitial cells of Cajal, the same Cajal. So Cajal was interested in this. But more recently, in the 1980s, this technique got popular, of placing electrodes on the abdomen and measuring that oscillatory signal. And the idea was very simple. You slap 3 electrodes on the abdomen. That's going to generate one waveform. And you look at that waveform and you see what frequencies are dominant. And you should see that 3 cycles per minute, or 0.05 hertz, is dominant. And if someone complains of constipation or food stays in their stomach a long time, maybe it's because when food comes into your stomach, what's supposed to happen is that your stomach senses that there's this expansion, and then those neurons tell those pacemaker cells to get active. They generate those action potentials and contractions occur. That would mean you would see more energy at 3 cycles per minute, or equivalently 0.05 hertz. So after when someone eats a meal, you should see more energy. The extent to which there's more energy, maybe that can tell us something about how your digestive system is functioning. Good high-level idea, but it turns out that there are many publications that came out that were pessimistic that basically showed that this readout is completely inconsistent with anything that you measure invasively with clinical gold standards. And so this ended up being having a very negative connotation. In fact, this technique, the electrogastrogram, is not taught in medical school. No one here in the audience, I'm guessing, has heard of this. And people tried to get at this, but they didn't get meaningful information. But we were ambitious, and just because of that, we didn't slow down. And so basically what we were able to do is that we were able to look through the literature and identify what some of the key limitations were. And at a high level, there were 3. And one of them is that different from the heart, it turns out that everyone's stomach can be in a different location. And that's crucially important because the way people were thinking about this in the 1980s is you just take, you go halfway between your belly button and the bottom of your rib cage, place 1 electrode, and then you go a few centimeters to the left and to the right, and that's how you slap your 3 electrodes. But if you look at these 4 pictures of these CTs from patients at UCSD, notice that those 3 red dots, half the time, are not even over the stomach. So it turns out the placement of your stomach relative to your, your belly button and your rib cage can vary quite a bit, which is different from the heart. And so we have, and so half the time people are not even recording signal from the stomach. Not surprising, if you try to interpret it, you don't get anything meaningful. Now, another challenge was that, as we know, placement on the abdomen, very slight movements that we make, movements that we don't even perceive, generate big muscle contractions that elicit these huge artifacts that can just generate lots of noise in the signal. And so basically the idea that we came up with was to use a multi-electrode array, because if we have a multi-electrode array, we have a higher chance of covering the stomach. And going all the way back to the days of my PhD, eliminating noise from signal, that's my bread and butter, right? I can do that in my sleep. So we're able to develop appropriate methods to eliminate the artifact from the signal. So we then went down the course of trying to validate some of these techniques. And so the clinical gold standard in gastroenterology, and I'm sure some people in the audience have gone through this, if you go to your family doctor, they try to put you on different medications to deal with your nausea, your pain. If it doesn't go away, then they refer you to a gastroenterologist. They might do an endoscopy to make sure that there's not some physical type of blockage due to inflammation or something. Then after that, if they don't see a problem there, they're going to send you over to nuclear medicine to get an imaging study. And basically what they do is they make you eat a radioactive egg sandwich, and then they image the egg as it goes through your stomach as your stomach empties it. And you should take about 4 hours for this to clear out of your stomach. And so they wait and they see what percentage of the egg sandwich is left at 4 hours. And that's a measure of your gastric emptying and whether or not it's delayed. So since the egg sandwich is radioactive, the imaging itself actually does not, it's not like an x-ray. The imaging is not subjecting you to radiation. It's just that once eating the radioactive egg sandwich. So what that means is that we can image as fast as we like. So we partnered with a radiologist and we actually imaged every second. We took images every second. We're not exposing them to any more radiation while we simultaneously had our array on. And it turns out that we can image individual contractions and locations of the stomach. And we're also getting this electrical information, and then we can pair them up. And we can look at the frequency of contractions that we got from the images, which is a mechanical readout, to compare that to our electrical measure, and they're commensurate. Moreover, we can look at the oscillatory signal that we got and compare that and the phase of that signal to the times of contractions, and they're spot on. And so in the bottom right picture, the red vertical lines are contractions that were measured from imaging, and these blue curves that I'm drawing you basically come from the electrical signal, and you can see almost complete alignment. So this is a way for us, there's a bit of a Rodney Dangerfield going on here where this readout doesn't get any respect, and so we have to do lots of validation to earn people's respect before we could begin to play offense with it. So another role of us playing Rodney Dangerfield is looking at a different invasive measure where they actually, believe it or not, sometimes they take a catheter and they shove it through your nose, and it goes down your esophagus and into your stomach, and it measures the pressure in your stomach. And so what we did is while someone was being subjected to that, we also placed our electrodes non-invasively over the abdomen, and we basically got a readout. And basically the takeaway lesson is that the blue curve that you see is coming from that pressure signal with the catheter. The green curve is coming from our electrical readout, and in 11 subjects, the pictures always look like this. They're very close. You can statistically quantify this, that they're commensurate in a statistical sense. So this is further evidence that what we're picking up is not nonsense. So the next limitation that we got interested in trying to address is that it turns out that when you take a look at people who have some of these diagnosed GI conditions, there's a bit of the nature in which the propagation that's going that gives rise to this. And I guess one way to think about this from 30,000 feet is suppose that someone has reflux or is taking a long time for their stomach to empty. It could be that there's too much acid in their stomach, but maybe it's also that maybe the smooth muscle cells are not pushing downward. Maybe they're pushing upward sometimes. And as you can imagine, that's going to create a lot of discomfort. So what we got interested in doing is being able to measure the directionality that things were going. And the reason that we got interested in this is because there was some new cutting edge research that came out by some people that published in the most prestigious GI journal. And what they did is they took advantage that sometimes when people are under surgery for an open abdominal surgery, if the abdomen is already open, you can actually place electrodes right on the surface of the stomach. And when they placed electrodes right on the surface of the stomach, what they found was patients that did not have a diagnosis of a GI condition, you saw kind of this top to bottom electrical propagation as we would imagine. But actually for some of these people who are diagnosed with different GI conditions, you saw a variety of different issues. And so in this case, if you notice, it's not going top to bottom, it's actually going bottom up. This is called an abnormal initiation, very analogous to the terminology that's used in cardiology. And so the takeaway lesson, if you think about this, is that you should have a wave that's going from the top of the stomach completely downward. But in some situations, the initiation point of the wave is in the wrong place. And so it's propagating in the wrong place. And that's what gives rise to these conditions. So with this in mind, if we want to capture this type of information, you can't just have a single waveform. You need multiple waveforms. And so what we did is we took advantage of this array. And we're not we're not only using this array to make sure that we're covering the stomach, but we're actually using the readouts from multiple electrodes and looking at the phases as they relate to distance. And by doing some very basic physics, and I won't go into details of this, but doing some very basic physics, we can actually look at the direction the wave is propagating. So we can infer that just from an array of electrodes. And we can dynamically track this over time to see what direction the wave is propagating. And so with this type of information, there's all sorts of fun that we can do. And one of the things that we did is we were able to consent patients who were diagnosed, very detailed characterization of their GI disorder, as well as controls. And what we did is for each of those, we had their CT images. And so we knew what the normal direction, going from the esophagus towards the small intestine should be. And so we know what that normal direction is, and we can look at a percentage of the time that the waves that we read out are going in that direction. So what you see in each of these plots is a circular histogram. So it's a histogram, but with respect to 360 degrees. And so for this control, you see most of the wave is going around 180 degrees. But for this patient on the right who has what's called gastroparesis, which means it's taking a long time for food to empty the stomach, notice that virtually none of the time is it actually going the direction it's supposed to. Most of the time, it's actually going retrograde or the wrong time. So we now have a quantitative readout, which is the fraction of time that it's going in a direction towards your small intestines. And remarkably, what we were able to do is we were able to look at every patient and look at the percentage of time that it's abnormal, and we can compare that to a well-known clinically indicated symptom severity index. So there's a questionnaire. How much reflux do you have? How much of this? How much pain? Abdominal pain, this and that. All this gets tallied into a score. The closer to 0 means the fewer symptoms you have. The closer to 5 means the more extreme your symptoms are. And what's remarkable is that if you look at all of the controls who did not have a diagnosis, notice that in all of them, the percentage of abnormality of the waves on the x-axis is to the left, and also their symptom score is low, right? So they're all sort of in the bottom left. All of the stars are in the bottom left. What's perhaps is more interesting is that indeed there's lots of variability for the patients who had different conditions, but notice that there is a very strong association between the percentage of abnormal waves and the symptom severity. So it turns out that this is huge in the GI field because in some sense, the GI field is in the Stone Ages in the sense that there are very few objective measures of GI function that correlate with symptom severity. And as you can imagine, as a doctor, that's a big problem, right? Because I can do this objective measure that's very invasive and it tells me something. For example, how long does it take for this food to empty your stomach? It's called your gastric emptying test. There have been numerous studies that have shown that that readout does not correlate with symptom severity. It's unfortunate because you just ate a radioactive sandwich. So having an objective readout, because if you have something objective, then you can do an alteration and see how that objective readout changes. And ideally, the change in that you track should be in alignment with symptoms. And so indeed this is. And so what we presented on this summer actually won an award, the best presentation of this type in the stomach section at an annual conference that we presented on. And so, so we now have this ability to extract information that is more clinically actionable. But the other aspect about the digestive system that's, very much like the heart and very much like blood pressure is the issue that when I have these symptoms associated with my digestive system, they're not constant. They're not all the time. They might come for a while. They might go away. So suppose that I made this appointment with my doc, and I'm so excited to meet with them. And maybe when they measure me, if my symptoms are there, they'll get a sense of what goes on. But suppose that I made this appointment 2 months in advance, and the day I show up, I'm not having these symptoms. So whatever they measure might not be reflecting what I have. Wouldn't it be nice if we could have something that could actually measure the dynamic function, not only during this office visit, but more generally? And so what we got interested in to be able to do that is to try to build something almost like a Holter monitor. If anyone is familiar with the Holter monitor, which is a way to measure the heart continuously, could we build something analogous, almost like a Holter monitor for the stomach? And so we built one. And so this is a wearable ambulatory system for 24 hours. And so, you can sit down, you can eat, you can walk in this, because we can do all the signal processing to reject artifacts. We can clean that up. We also built a smartphone app associated with it, because what's important is that we can track what's going on with your digestive system at the time points in which you have symptoms, or after you ate a snack, after you ate a meal, before a bowel movement, when you went to sleep, etc. So having these events is crucially important as well. So in this process, we actually were the first group to be able to get a 24-hour monitor of the digestive system, non-invasively, and we're able to discover some interesting things. And so here's sort of what a normal control looks like in their 24-hour pattern. So what I'm showing you up top is a time frequency plot, and frequency, remember, 0.05 is the money. That's the money for the stomach. And what you notice is that redness kind of ebbs and wanes. It's not always red. It goes on for a while. It goes off for a while. If you notice at the bottom, we have these vertical lines where events occurred. So, for example, green vertical lines associate when a meal occurs. And what we see is that after a meal occurs, after a bit of a delay, you see a lot of red in the signal, which makes sense because the contractions are occurring. But we also found some other interesting things. And in particular, when you go to sleep, there appears to be a lot of activity early on, and then towards the latter stages of sleep, it kind of dies off. So we're able to track all this sort of dynamic phenomena that arises from using these systems. And we came up with this terminology that we call gastrodynamics. The reason we do this is, in other fields of medicine, there's something called urodynamics for urology. So the idea is come up with an analogous terminology. And what we can start to do is to build almost like reports that you can imagine. The doctor could send you home to wear this. We come back and a report is generated and an interpretation can be made to figure out a treatment plan. And what we can do is we can zoom in particular in the vicinity of when a meal occurred, and we can see how long of a delay was there before we see that increase in those contractions associated with the meal. We can look at symptoms. There's a variety of things that we can do with this type of technology. And what I wanted to do was to give you one example of how this technology really benefited a patient case with my collaborator, Dr. Kunkel. And so the takeaway lesson is that we had this 68-year-old patient who had lots of bloating, and he got full very early. He's a retired aerospace worker, played a lot of golf. His symptoms were that his bloating was better in the morning, but got worse throughout the course of the day. At night, his wife said sometimes that he looked pregnant. He had the sensation of always being full and just feeling sick. And if he rotated side to side, he could actually feel the food splashing around. So what made this case complicated is the fact that so he has pancreatitis. He's also a type 2 diabetic, and he takes a variety of different medications to treat this stuff. So the type 2 diabetes is important because it turns out that if you have type 2 diabetes, about half of diabetics actually have delayed gastric emptying, and that's well known. And so a lot of GI docs, when they see that you have diabetes and you're having these digestive problems, they think that there's a causal link, and there may be a causal link because this, lack of ability to regulate glucose, that can actually damage some of the pacemaker cells. It can create lots of other challenges, which could explain. So maybe, the contractions are not occurring the way they're supposed to because of your diabetes. So my colleague took a look at his CT scan and look at how bloated his stomach is. It's just crazy. It's like a big bloated balloon. And so the question becomes, what would you do? And I won't bore you with the details of this, but would you try to provide him some type of medicine that helps treat his diabetes? Another issue could be that maybe it's his small intestines and not his stomach. Maybe he has a little bit of bacterial overgrowth in his stomach. Could you, prescribe him a diet that avoids certain types of foods that worsen that condition? Should you just give him something that's a prokinetic that encourages more of the contractions? Or should you actually give him something that only manages symptoms? So they do this sometimes. They cannot figure out what the problem is. So they basically give you something so that we're not treating the function, we're just managing your symptoms. But my colleague said, aha, what if we tried something else? What if we actually tried the ambulatory monitor just to see what happens? So when we did the ambulatory monitor and you look at this picture, there's something that's very glaring. And so if you look at our case here, notice that the 0.05 is extremely red the whole time. It doesn't ebb and wane. It's not like it's only red after a meal. It doesn't die down when you go to sleep. It's always on. And so what this means is that those pacemaker cells and the contractions, the smooth muscle cells, they're just always pushing aggressively. They're never pausing. And that's suggestive that something downstream is probably clogged. That's suggestive that there's a blockage or an obstruction. And so what he did to try to determine that is, it turns out in between our stomach and our small intestines, there's a little gatekeeper there, and it's called your pylorus. It's a sphincter. And so sometimes that thing can be, something can be wrong with it. So after he saw this readout from our ambulatory system, he sent him over to pathology, and they basically got a piece of the bottom of the stomach near the pylorus. And when they did the biopsy, they actually saw some really weird, groups of 4, groups of 8. And when they looked at the details, there are these Sarcina organisms that basically created like a small little infection, which created inflammation, and that inflammation created that blockage. And so it turns out that it wasn't the cause of his problems was not his type 2 diabetes. It was some infection that he had that created this inflammation in the gatekeeper area. So with that, it turns out there's a quick fix for this. You can send them over to surgery, and they can do a surgery to connect the small intestines to the stomach and to bypass where that inflammation, that scar tissue is. So here's what a picture looks like before the surgery. And after he had the surgery, here's what the picture looks like, a whole lot better. And then lastly, what we did is we actually did an objective assessment. We actually did a 24-hour monitor before and after the surgery. And indeed, you see a reduction in the severity of the redness. Most importantly, his symptoms went away. So this is a great example of a case that, had it not been for us using the ambulatory system to see that persistent redness everywhere, he might have went down some very different treatment path trying to focus on the diabetes and would not have caught what the real issue was. So that's sort of just an example of how this has benefited patient care. And in terms of other steps that we're going with this technology is, remember where I started, were these thin, flexible electronics, although what I've showed you with GI so far didn't show you that. So I'm sure some of you were wondering, can we build the flexible electronic systems to track the GI system? And it turns out the answer is yes. And so we had to actually change the way we built some of these systems. And this is the beauty of physiology and medicine. Remember, everything I said about the stomach is that the money is at 3 cycles per minute, which is 0.05 hertz. 0.05 hertz is almost DC. That's almost 0 hertz. So it turns out if you use the same type of electrodes that we use to measure the EKG or the EEG, it turns out that those are sensitive to DC noise, and so we don't get a clear signal. So we had to change our electrodes, knowing what frequency we're focusing upon, but we were successfully able to do it. And when we did so with these thin adhesive electronics, we can measure the gastric signal. So we also have an ongoing collaboration with a famous key opinion leader gastroenterologist at Stanford, because one of the things that you guys might be wondering is, now that we have an objective system that is completely non-invasive, what's cool about this is that you can provide a treatment, and then you can look at pre and post of treatment to see the response. And so one step in that direction that we're doing is that she has a clinical trial where she's using an FDA approved device that you mount onto your neck. It's a vagus stimulator. It's FDA approved for treating migraines. But it turns out that the mechanism of action is such that it also could benefit the digestive system because of the role of the vagus nerve and sympathetic, parasympathetic, quote unquote, for people who know what that is. So what we were able to do is we were able to get approval at Stanford to work with her device. And so in one of her patients, what we have is that we can do the 24-hour monitoring, and where those vertical lines are correspond to where the vagus nerve stimulation was. And it turns out with our device, we can also measure heart rate and heart rate variability. And what we were able to do is to take a look at when the vagus nerve stimulator was turned on and when it was turned off, and we see some very interesting things that occur. In particular, what we notice is that we see an increase in what's called parasympathetic activity, and that's manifested by a decrease in heart rate and an increase in the gastric signal. And delayed afterwards, we see sort of that resetting where we see an increase in heart rate and a decrease in the signal. And based upon the mechanism of action of what we think the system is doing, this is in alignment with this. And so this provides an opportunity for us to assess the efficacy of a treatment such as a stimulator for these conditions. Now, something else that you can imagine doing that I actually am tasking some undergraduate students at our university. One great thing about undergraduate students is that once you can almost make something almost like a commodity, you can just allow them to use their creativity and how to use it. And so some of the undergraduate students came up with the idea of, well, you may or may not have heard that there are all these companies that build very simple apps where you can take a picture of your food and you can see how much nutrition is in your food. You can see how much of this, and with deep learning and artificial intelligence, they're getting better and better at this. So let's imagine that. I always find that I forget why, but sometimes I have a lot of gastric pain or a lot of nausea when I eat certain foods. What if now I can start to take pictures of what I ate? These algorithms can infer how much animal fat is this, how much protein, how much of all this is, and I can combine that with the electrical signature of my digestive system. And can I start to pattern match to see that maybe it's the case my digestive system responds more to this type of diet and worse to that type of diet. And so this is an ongoing project that we've had some undergraduate students at our university working on. One previous success that we had that's suggestive that there might be an opportunity here is that we took a look at, so it turns out one of the students that did research with us actually was a type 1 diabetic, and he had a continuous glucose monitor. And so the continuous glucose monitor actually allows you to stream the glucose to your phone and you can store the data. So we got his continuous glucose monitor and simultaneously while we placed our device on him, and we did some very controlled experiments where we kind of know what should happen to track and to see what dynamics we see. So what's very cool about this is we first had him eat a bagel, and so that's that first green vertical line. And what you see is it takes a while for that to sort of enter in the bloodstream and for the glucose to go up, so there's a delay. We don't see that much of a change in the gastric activity also. But then he drank some orange juice, and you drink orange juice, that's just a big bolus of sugar. And so you see this glucose spike right away. And so we know that blood goes into the bloodstream after the small intestines, right? So the small intestines gets everything into the bloodstream. So it turns out that the small intestines, which is after the stomach, has a feedback loop to the stomach, and it makes a lot of sense. And what it determines, if your body determines, wait a minute, my glucose is starting to get too heavy, guess what it tells the stomach to do? It tells the stomach to pump the brakes, to slow down on those contractions so you don't bring more glucose my way. And so what you notice is you see that as glucose starts to rise, and notice that as his glucose is rising, the activity in the gastric signal is going down. And so those are the brakes on his small intestines, sensing that this glucose is increasing. Then he gave himself some insulin, and after he gave himself some insulin, you see that the glucose starts to stabilize, and what happens? The GI activity starts to increase again to process that bagel. So this dynamic process we're able to see by measuring the continuous glucose monitor and the GI signal. And so we're collaborating with a type 1 diabetic who leads a nonprofit who has all of these interests in timing of meals and timing insulin after exercise, et cetera. So there's lots of fun questions that we can ask by combining the readout of the continuous glucose monitor with the gastric signal. And so hopefully this gives you a sense of a variety of different opportunities that we can now do. And so more generally, I've already done lots of research in sleep. We know that things like stress can cause ulcers, but there's the brain-gut balance. There are all these interesting questions that we can now ask by combining readily available technologies with now this new modality associated with the electrical activity of the digestive system. And those are the areas that we're pursuing. And so, at a high level, this is kind of, obvious, but this creates new opportunities for doctors to assess patients. I mentioned this whole issue of treatment response. The treatment response need not be a vagus nerve stimulator. It could simply be a new type of drug that we want to use to assess how well this works with your digestive system. There's all sorts of opportunities for how these things can intermingle. And because we can digitize this information, we create a common currency from which we can exchange, we can perform artificial intelligence, we can improve lives. And so where I'd like to conclude is by just acknowledging my research group. This is a very old picture of a research group, but what I love about this picture is that there's a lot of things you can see, but there's one thing you cannot see. So what you can see in this picture is you can see gender diversity, you can see ethnic diversity, you can see nationality diversity. But what's not in this picture, which I think is the most important, is that our research group, we like to bring people from very different mindsets and different trainings. So some people in our research group have PhDs in biology. Some people have bachelor's degrees in electrical engineering, bachelor's degrees in bioengineering. So by bringing people together who have very different perspectives and trying to attack a problem, we get insights from everyone. And so that can't see in this picture, but that's what I'm the most proud of. So with that, I conclude my talk. Thank you.
So thank you, Todd. We have time for some questions. There is a procedure for questions. For those of you who don't know, there are people with microphones that have foam covers in different colors. And keep your hand up long enough for somebody to see you who has a microphone and bring it to you. And I will point to you and call out the color of the microphone. And then you can stand up and tell us your name, tell us if you're a member, and then ask a question, save the discussion for the social hour. Okay, good.
My name is Colin Alberts. I'm a member, and as it happens, a Michigan man as well.
Go blue. Blue.
Indeed, go blue. Got a question about RF interference, and want to see how well what that is playing in the engineering of these devices. Because I remember a few years back there was a discussion when they did allocate some spectrum to M bands, and I suppose that you're using the same 2.4 gig band that were allocated to M bands back then. But I didn't hear a lot about interference. But it seems to me that you're building devices that are extremely low power, using a very narrow channel in hospital rooms, which, let's face it, are extremely emitter-rich environments. And I want to know, how are you encountering problems with spectral interference, and how are you dealing with them?
Excellent question. So indeed, right now, so the way we wanted to structure these thin, flexible electronics is because, remember, I myself am not originally a material scientist or a nano engineer. I'm really an electrical engineer who then learned physiology, who got involved in technology. But my focus on technology development is extremely focused on trying to solve a problem that we've identified. And so what we realized is that if we want to be innovators in this area, maybe what we can bring to the table is innovative approaches so that we can be backwards compatible with existing chips, and we can just integrate them in a manner that allows for flexibility and mounting onto devices. And so our system is using a Bluetooth chip made by another company. There's some clever things that we had to do with the antenna, and it actually turns out that it's a bit surprising, but if we're careful with how we design that antenna, we can actually get better signaling performance than antennas that are mounted onto typical substrates from our experiences. But the Bluetooth chip and the management of interference and all those algorithms, that's just using a third-party piece of software. So we've had success. One of the things that we have found is that the distance, depending upon what environment you're in, you have to be a little closer to get reception. But we're really, outside of the antenna development, everything else is just building off of existing engineered solutions, as long as they're packaged in very small chips.
Yeah, the blue mic.
Yes, hello. My name's Dan Elton. I am not a member. It's actually my first time here. And my question was, I'd like to hear more about how the wearable biosensors could be used for EEG, which I think you mentioned somewhere at the beginning of the talk.
Yes.
And I'm really curious what the potential advantages of things you wear on the skin would be as opposed to just a headrest, headset, or a gel-based system?
Excellent question. So my original interest in building these flexible electronics was specifically for targeting the EEG application. So we have done multiple studies in EEG. For instance, one of my PhD students who recently graduated was interested in the problem of, imagine if, I don't know if anyone has ever had to, if you're worried you might have sleep apnea and they have to send you to a sleep lab and they instrument you with all this stuff and it's extremely uncomfortable sleep. So it's a great example of the story that in the process of measuring a system, you undoubtedly perturb it. Going to do a sleep study is a great example of that. So what we got interested in is, imagine we could get, commensurate types of information in the comfort of your own home by just slapping a forehead, a patch on your forehead. Could we do EEG? Could we actually stage the EEG during different stages of sleep? And so we had a great success in doing that, and we've published on that, and we have another manuscript we're going to get out. So within a very focused context of thinking about staging sleep, for instance, we've had success in doing that. It's a combination of where you place the electrodes on the forehead, because depending upon what you're trying to measure, where you should place the electrodes is crucially important. And hopefully that message came clear, because it also applied for the stomach, right? So also for the brain, depending upon what you want to measure, where you place the electrodes is important. Now, if you think about what you said, the conventional system, which is what I call a shower cap, right? If you've ever seen, an EEG study where they put all the things on you, put this thing on you. So that's cute for a clinical study, but no one is going to wear that all the time or wear that in the comfort of their own home. But that is getting signal from many locations. So there's a trade-off in that if the signal that you want is not near somewhere where you can just place something on the skin, the solution that I'm talking about is probably not going to apply. But if you now limit yourself and you say, well, what aspects of brain function, prefrontal, et cetera, things that are, if we focus on the forehead, for instance, then we can ask ourselves, what subset of things about brain function that are important clinically sort of are modulated or, could be measured in the forehead, and then ask the question, can we do it with these sensors? And that was the sort of philosophical approach that we took. There are other areas as well. You could go behind the ears, et cetera. In general, I don't think that the patches that we've developed are going to be able to have the same fidelity as a shower cap, because you're just placing sensors in different locations. But what is interesting is if you're focusing on trying to catch an epileptic seizure, that's kind of an all or nothing event, right? If you don't catch that, there's a big problem, right? But in other situations, you might be wanting to track something about, the quality of their cognitive function over time, et cetera. And if there is a gray area, what you might be able to benefit, even if you're not at the optimal location, if you're slightly suboptimal, but if you have the benefit of comfort in tracking over a very long period of time, that still could be advantageous to a shower cap. So that's the philosophical approach that we take, and we look at problems one by one, depending upon what we're trying to attack.
I think we had the yellow microphone.
Hi, my name's Nick Becker. No, I'm not a member. I have around 3 points for you to talk about.
I'm listening.
You mentioned
wait.
your
I don't know
student.
if you get 3. No, I'm just kidding.
I'll keep it quick. You mentioned the student with diabetes type 1 with the continuous glucose monitor.
Yes.
I was waiting your whole talk. Are you going to reduce, a miniature glucose monitor? That's point 1. That'd be a good invention. 2, white blood cells, and perhaps levels of blood acidity. Maybe have 2 probes into the blood. Something that could be measured, because it sounds like you're mainly talking about sound, hertz, electrical voltmeter, sound meter, microphone. So that's the second part. And then the third part, one of your slides had insurance. How could this, like the monitors, the black box on your car or plane, hey, you're driving safe, let's give you a discount. How about this? My mom eats ice cream 2 a.m. I know her glucose is shooting high. The next day she takes her blood. Oh, it looks good. Look at my level. Playing games with doctors, If you could have these monitors, how would you have it work with the insurances?
So, do I respond to that or no?
Do your best.
So, your third point, I think you're spot on. You're spot on with that, and there's a lot of interest in that regard. For your first 2 points, if we summarize both of them, I think the question you're asking is, do we want to possibly try to measure stuff that's inside the blood or inside the body? For starters, we were focused on being non-invasive because it's just such a beautiful story. There's no risk, right? You're just slapping something onto the body. There have been some people who've tried to be fully non-invasive, but to infer stuff in the blood. So for example, some people have tried to infer glucose from sweat, which you could pick up right on the surface of the skin. I'm very fortunate to be at UC San Diego where we have world-class experts. So one of my colleagues is a world expert in the type 1 diabetes problem and tracking glucose. And when I heard people begin to talk about this, he cautioned me very carefully because he said, indeed, there is glucose in your sweat, but it turns out that the NIH has spent over $1 billion trying to fund people that can take that information to correlate it with what's in the blood. But so far, no one has been able to do it. So if someone can measure glucose in your sweat, that's not necessarily the interesting question. The interesting question is, does that associate with what's in your blood? Because that's what's important, what we care about. And as of now, as far as I understand, no one has tried to solve that problem. So trying to go completely non-invasive to do that may be very challenging unless you use a very different form of physics to do it. What could be also interesting is what if you take these thin devices and embed them inside the body? We could do that, but I'm cautious. Because remember, I'm originally an electrical engineer, data scientist. If we start getting involved with there's these issues of your body, the immune system, rejecting foreign bodies. So I'm listening when I hear people give ideas, but there's an activation energy threshold that has to be hit before I'm willing to take the risk to do it. That being said, this is such an exciting topic now. So since 2011, when these types of articles came out that we published, there are so many people that are now building thin, flexible electronics, some of them putting inside the body, and some of these people are materials experts. So some of these things, I will defer to others. Jack of many trades, but not all.
We're going to go red, then we're going to go blue, and then we'll do yellow. 1, 2, 3.
I'm Ron Summers, and I'm a member. As I was listening to your part about the gastric analysis, it reminded me of capsule endoscopy or the camera pill, and there are many similarities between the camera pill and the technology that you're using, including the transmission of signal and the monitoring of gastrointestinal processes. I was wondering if you could talk a little bit about how the capsule endoscopy might have informed your research and how maybe your work might inform the development of camera pills.
Excellent question. I should have included something on that, but it turns out that early on, in partnership with Dr. Kunkel, he does some of these capsule studies on patients, and so we did some simultaneous studies with the capsule and our device. One of the issues about the capsule that the doctors don't like, or say are not completely happy with, glass half full versus half empty, is that you don't know exactly where it is because it's actually going through your body. So at a high level, because it measures acidity, you know when you're in the stomach, you know when you're not in the stomach because the pH changes. But outside of that, you don't know exactly where you are. So if you're measuring this pressure or this other information, you can kind of approximate, but you don't know exactly where it is. And so that sort of creates a limitation. I think what is interesting about this is to think from the perspective of 2 + 2 = 5. So one of the things that we've been trying to wrap our heads around is what if you could simultaneously use that with our device, and by combining both pieces of information, is there much greater that you can get? And that's an active area of investigation. But I would say at a high level, one of the challenges with these pill-based systems is that you don't know exactly where you are. And so, sometimes location is important.
Zainab.
Hi, I'm Zainab, and I'm a member of the society. So the applications that you've talked about, the technology you're creating is allowing a lot of different diagnostic approaches to things that are difficult to diagnose. So one area I know in which diagnostics is difficult is pain.
Pain. Okay.
People don't know how to report their pain accurately. You have no way of measuring pain levels in nonverbal people, babies. Has anybody approached you? Have you approached anybody, or is there anything?
That's a very, very exciting area. We have some ideas on that. I can leave it at that. We can chat more afterwards, but it's a very exciting topic. especially if you think about the opioid crisis, all these different things. There's lots of innovation taking place. I'll give you one example. One of my colleagues at UC San Diego, we hire all these brilliant young people. Some of the young people we hire, I ask myself how I could not have even come close to get hired in how things are. But one of my young colleagues who just got recruited to UC San Diego in my department, bioengineering from Hopkins, his PhD student has invented some way using this CRISPR technology some of you may have heard of. They have some way of being able to block the transmission of pain to your brain. That is absolutely fascinating, and they're spinning out a company on it. So that's the problem of if you have some type of persistent pain or whatever, can you block it? I think the question that you're after is, can you measure it? There's some tricky things about that because the measurement of pain could be done in some areas. It could be done in the brain, or it could be done in the periphery. There are some details that have to be ironed out, but within some context, we have some ideas on that we want to explore, and I'd be happy to chat with you about it more during the discussion.
My name is Scott Matthews. I'm not a member. I have two quick questions. The first one is, if someone has some gastrointestinal or digestive problems and they want to either maybe volunteer for a study or get access to one of your ambulatory systems, is there a method for doing that? And then my second question is, can you say a little bit more about how you separate abdominal EMG signals from the gastric, from the signals that you really want? I'm not talking so much about motion artifact where electrodes might move or contacts might change, but actual real EMG signals that are just coming from other muscles that aren't the muscles you're interested in.
Excellent question. So for your first question about can you be a volunteer in the study, I'd be happy to chat with you more offline. We're partnering with more and more people across the country, so there's more and more opportunities to do that. For your second question, the beauty is that the source of the gastric signal is in a very specific frequency band, and if you take a look at the myoelectric signal associated with EMG, the frequencies associated with that are typically very different. So you use that information to separate things with appropriate signal processing. Yeah.
Red microphone might be the last question. If you have a question, raise your hand. Yellow over there. And blue over here. Okay, got it. Red, blue, yellow.
Will Angel, I'm not a member. Could you talk more about the commercialization of this technology, specifically what we can expect it to cost as it moves more towards mass production, and the reliability and longevity in terms of battery life of the systems? Thank you.
Are you talking about the flexible electronic systems or the GI more specifically, or?
In general, specifically the flexible sensor systems.
Yeah, so we have multiple patent filings on the flexible electronic systems. We have been trying to partner with some companies, and for example, placement of the individual chips, we've been able to do that successfully with the San Diego company, with using their existing equipment to do so. So there's multiple ways that this can go. I'll give you one example. The project associated with the newborn babies and temperature, so that's actually manifested here in the developed world, like the neonatal intensive care unit in San Diego or in San Francisco, but also imagine the developing world. It's a big challenge. And so we have a project that's supported by the Gates Foundation, and they have a very serious interest in not only being able to demonstrate this, but being able to demonstrate this at extremely low cost. And so it very well be that in the process of them trying to keep us honest, we'll be able to squeeze it down even further. I didn't spend too much time talking about batteries, but one thing I will say is that there's so much innovation taking place with battery companies now, and they're increasingly thin, flexible batteries. The key thing that we try to focus on is making sure that the energy consumption that we use is appropriately managed. And there are ways that you can do this with software, powering things down, powering things back up. So there are ways that we're doing that in what's called firmware to do that. So I think that addresses your questions, the energy management, and then luckily having someone like the Gates Foundation support you really forces you to think very carefully about not only is this an experiment, but could this be widely deployed and cheaply, because they have a vision for this being not only useful here, but in the developing world. And so that's part of how we're always thinking. So I think that might help push things in that direction too.
Mr. Blue.
Mr. Blue.
Michael Sitter, I'm a psychologist.
Could you-
I am not now. and
Wait,
have never,
wait, can't hear you.
Hi, Michael Sitter, I'm a psychologist in Bethesda. I'm not now and have never been a member. I've not been this excited on a Friday night that didn't involve a date. This is great. I do biofeedback, brainwave, skin conductance, muscle tension. And the last I heard about any gut stuff was a dual head stethoscope where the clinician would listen and coach the person who was listening to their own bowel sounds, gut motility, and somehow train them. I bought this stethoscope but have never used it. But this is a lot more exciting. And I'm wondering if there's any equipment vendors that have embraced this yet in the biofeedback field.
Not yet, but we are collaborating with a couple of groups on looking at biofeedback for a variety of purposes. Brain gut imbalance, and by using biofeedback, can you help get things better in tune? So that's an active area that we're in, but we haven't been contacted by equipment companies as of yet.
You will be.
All right.
Thank you. Appreciate it.
Okay, we have yellow, and then if you can bring the red microphone over here. Oh, okay, get the blue one over here then. Mr. Yellow.
Good evening. My name is Erez. I'm not a member, but I did bring my 2 teenagers to this meeting the first
great.
time. So he stole one of my questions about batteries, but in your experience, how long do they last? And related to that, do you think those devices can be reusable or they are once?
Love it. So the how long they can be used is completely application dependent. So, for instance, for the project with the newborn babies and the neonatal intensive care unit, for there, if you took it, how often that they want to measure temperature, that would be clinically useful. It's on an order of a couple times an hour, a few times an hour. And so with that, what we can do is we can power down the device and then turn it back on, et cetera. And so with that, with an appropriate battery, we can spec out the duration of it. And the great news is that, they would love to be able for a baby to wear this for 2 or 3 days, and then you can let the natural process of the skin exfoliation for the stretch of the adhesive device to come off. Because another issue about newborn babies is that their skin is so fragile, especially if they're premature. So it'd be better if it kind of naturally falls off with the exfoliation of skin. So based upon their needs and what we're able to do, we can deliver on that now for that temperature sensing application. But if you think about something where you're recording from many electrodes and you need to record many times per second, so everything is application dependent. I'll leave it at that. Your second question was about reusability. And again, as I mentioned before, how the Gates Foundation people breathing down our neck, right? They had been breathing down our neck about questions of reusability because that could significantly reduce cost. And one of my brilliant engineering students has recently come up with an approach that allows for the component of the device that's more expensive to be reusable, but it can still be sandwiched inside of disposable stuff so that you don't have to worry about germs and things along those lines. So we basically have a hybrid solution with a reusable component, but what's adhering to the skin is disposable. And there's a saying that necessity is the mother of all invention, and that's exactly the story here. We would not have thought about that had it not been for these people keeping us honest. Yeah.
So we'll have Marie and then James, and I think then we'll close out. If people would stop turning the mics off, it would be very helpful.
Here we go. Hi, I'm Marie Burton, not currently a member. I had a question for you. I think you've talked a little bit more broadly about this, but you've spoken particularly about monitors that are specifically read by professionals. Mm-hmm. We've come certainly a long way from the old Holter monitor, I guess, but I wondered if you thought about a continuum between so many people are now empowered by wearing wearable sensors. I spoke to a patient today about the fact that we had no ECG on file for him, and he glanced at what looked like a wristwatch. He said, "Well, I can tell you right now, I'm in normal sinus at a rate of 78." And but is there a tension, do you think, between the self-empowerment that we have, and this ability to, at least in a limited way, self-diagnose, and the intervention or the surveillance by medical professionals, decision-making, that sort of thing?
It's a great question, and we definitely have an interest in that. I mean, there's the whole almost quantified self philosophy in groups of people who very much adhere to that. We think that there's definitely an opportunity there. And if you think about that example that I gave, that I have undergraduate students working on, where they're taking pictures of the food, and then from that, I mean, I think that is something that might be best empowered at the individual level, so that they can control their diet appropriately. So I think that there are some things that will be very natural for people to take a do-it-yourself attitude with, and other things will involve the medical establishment, and there's reaching the right equilibrium. There's another very explicit reason that we wanted to get the buy-in of the clinical community, and that's because that we're starting off underwater, in that this modality is not well respected, because when people started using this in the 1980s, they were not working with engineers, and so the paradigms that they developed were flawed in many ways. And so all those readouts were then shown subsequently to have no association with invasive, clinically accepted measurement procedures. So if you talk to some docs who are experts in motility, the first thing they do is they roll your eyes if you mention the electrogastrogram. Like, yeah, that was a thing that was popular in the 1980s and it didn't go anywhere. It's like Theranos or something, right? So what we're trying to do is we're trying to resurrect Theranos, and this time we want to make sure that we publish, right? And we don't just get former secretaries of state on our board. We actually, get the experts to buy into it. So that's part of the reason that we're working very closely with the docs, is because we're starting off underwater, trying to do this the right way, right? So, yeah.
James, you get the last question.
Good evening. I'm James Heelan. I'm a member. I'm wondering if you've looked down the line towards long-term wear sensors to get data and information from infants, for example, and other individuals who can't exactly tell us what their symptoms are.
Yes.
So I'm wondering, if in 40 years, if I have grandchildren, can they just wear a sensor all the time to tell me what hurts, or like if they're hungry, or if they have to go to the bathroom? Like, have you thought about these things? And if so, what do you think?
We have thought about a number of these types of questions. I mean, another example could simply be, could you train an artificial intelligence algorithm to hear different types of baby cries? And there's many things, because parents have just this innate ability to listen to the baby and know what that is. Imagine if you could provide that knowledge to a new nanny or to someone at daycare. So it need not even be something measurable, but with the ability to use artificial intelligence, things along those lines. With these physiologic readouts, I think some things, yes. I think we have to be very careful, though. We don't want to think that technology is going to solve all of our problems, but I think in some context, the answer is yes. I very much like the baby story, because exactly what you said. They're, I think, the most vulnerable patient population, because they can't defend for themselves and they can't tell you what's wrong with them, right? So I very much like thinking about problems that involve babies for exactly that reason. And I think in some context we will get better at that. But I like to also be careful, because as a technologist myself, we sometimes romanticize with how technology is going to solve all of our problems. And I like to think more of how technologies can be wed with humans, so that we can enjoy being human more so. So sort of from that perspective, yeah. Thank you.
So before you go, thanks for this very interesting talk. I'd like to present you with a framed copy of the announcement of your talk, signed by all the members of the General Committee on behalf of all the members of the Society, and also a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. For you newcomers, PSW stands for Philosophical Society of Washington. And we call it PSW Science now because many people get confused with the word philosophical and think that we're going to be discussing Hegel and Socrates, which we might do after a few drinks, but our presentations are about science. So thank you again for a wonderful talk. Appreciate your coming all the way from California.
Thank you.
And before we go, there are a few closing announcements. Before we adjourn to the social hour, PSW depends on members and sponsors, and without our members and sponsors, PSW couldn't pay for this room and couldn't continue to put on these lectures that are free to you but are not free. If you're not a member, please consider joining. And if you are a member and you haven't paid your dues, please pay your dues. And if you have paid your dues, please consider giving a little more and becoming a sponsor and or volunteering to help PSW carry out these activities, which are done entirely by volunteers. There are no paid staff to put on these lectures. You can apply for membership on the PSW website by going to the upper right-hand corner on the home page and pressing the Join button. That will bring up the page that has the application form, which when you press it will, believe it or not, actually bring up a membership application form. You fill it out, pay your dues, and you will be notified of your election to membership. Or in the very rare case where for some reason it might not be the best thing, we'll get in touch with you. And if it turns out that you decide you don't want to become a member, we'll return your dues. But generally speaking, it's pretty easy. Just fill out the membership application form and you'll be notified shortly that you become a member. If you have any questions, please see Membership Director Lloyd Mitchell, standing in the back of the room and has a card that says Lloyd Mitchell, Membership Director, or Corresponding Secretary Robin Taylor, or myself. PSW is a nonprofit educational organization. Donations are tax exempt under Section 501c3 of the Internal Revenue Code, to the extent permitted by law. All PSW members in good standing, can wear the PSW rosette. And if you wish to purchase a rosette, please see the person at the rosette table at the back of the auditorium. The next lecture will take place, we had that one already, at 8 p.m. here in the Powell Auditorium on Friday, February 8, 2019. The speaker will be Raman Sundram of the University of Maryland, and his lecture will be on growth of the embryonic universe, interpreting the cosmological fossil record. The lecture is sponsored by PSW member Frank Robert. The rest of the spring schedule is as follows. We're not sure what we're going to do on February 22nd because we had a late cancellation, and you'll have to check the website to find out who the speaker might be. On March 8th, the speaker will be Ramesh Gopinath of IBM, and he'll be talking about blockchains, not blockchains in cryptocurrency, but blockchains in other applications. He's in charge of IBM's blockchain in commerce department. On the 22nd, Jim Garvin and friends of NASA will be talking about Venus. On April 12th, Mary Angela Lasante of Princeton will be talking about dark matter. Kim Janda from the Scripps Research Institute will be speaking on April 26th, and his topic is vaccines against drugs of abuse. We have a very special event on April 29th. Alan Stern, the principal investigator of the New Horizons mission, and Ron Eckers, who is the former president of the International Astronomical Union, will be debating the definition of planet. Now, as you might imagine, Alan is a big proponent of Pluto being a planet. So he is an advocate for a definition that includes Pluto. Ron was head of the group that decided to demote Pluto from planetness to what is now finally referred to as dwarf planetness. And so we'll have an interesting discussion really a scientific discussion, not just a debate of people screaming at each other like they do up on Capitol Hill. No, this is going to be an actual discussion of what are the criteria that you should use to decide whether a celestial entity is a planet or a moon or a comet or an asteroid. In this particular case, what makes for a planet? So it should be a lot of fun and very interesting. And then finally, we'll wrap the season up with a talk by Brian Keating of UCSD. Some of you may know. Brian is the author of a book called Losing the Nobel Prize, which is kind of a fun book. It does take some pot shots at the Nobel Prize, but it also is a sort of biographical account of some of his research. And I'm hoping he'll talk about cosmic inflation and not Nobel deflation. I know, it was terrible, right? The social hour ends at 10:30, after which PSW members and their guests meet at the Fairfax Hotel Lounge to close out the evening. The lounge is just across Mass Avenue. If you want to join us, please speak with me or our membership director, Lloyd Mitchell. Please use the side entrance to exit the building. And I will now accept a motion for adjournment of the 2402nd meeting of the Society to the Social Hour. Bob, Jay, do I have a second? I have seconds. Do I have all those in favor? Aye. All members opposed? There be up. Leave. I think I can say that the motion passes unanimously and the meeting is adjourned to the social hour.